Alright guys, so today we are going to do problem of the day for December 6th, 938, range of sum BST. As you can see, I've never done this problem before or seen. So, let's see. Given the root node of a binary search tree and two integers low and high, return the sum of values of all nodes with the value in the inclusive range low-high. Okay, so we have root 10, 5, 15, 3, 7, like this. And we want numbers inclusive 7 and 15. So you would do 10 plus 7, so 17, and then 15, and then that would be it. So you'd only traverse these 4 nodes. Since this is a binary search tree, I think we can do a little more efficient search. Okay. So 10, 5, 7, 6. Our low and high is 6 and 10. So let's go to 5. We know that we should not go to the left. So we go right and then add it if it's within that root. Okay. So let's talk about, of course, our goal. So the goal here, return the, or I should say our definition of the function, return the sum of values inclusive low high. Input root of the binary search tree, ram2, low of range, high of range. Output, return the sum of values between low and high. Okay, so we took a look at some examples, ran through these. Let's say we had a tree size 1, low high is equal to both equal to 1, then we say the sum is 1. Low high is both equal to 5, then we say the sum is 0. So that's an edge case. Now for the 0 node edge case, we don't have to think about it because it says here there's at least 1 node in the tree. Okay. Any negative values we don't have to account. So, and it says all node.value are unique. Okay. So let's talk about some pseudocode. First thing I noticed is that since it is a binary search tree, when we're looking for values to include, we can go ahead and completely ignore some branches. For example, my low here is 7. And if I go to the 5 here, I know that anything to the left of the 5, this 3 for instance, is not going to be in this range because it's going to be less than 5, which is all less than 7. So that's not going to be in that range. And same thing on the high side here, 15. I know nothing on the right is going to be in that range because everything to the right is going to be greater than 15, and that's not, and that's greater than our high value. So we won't search to the right, and we can repeat that for any node we quote unquote search. Okay, so the question here is, should we use a DFS or a BFS? The time complexity for both are going to be the same. The space complexity is what's different. For DFS, the space complexity is as large as the call stack because it's kind of a recursive algorithm. So it's the height of the tree, whereas the BFS is the width of the tree. I think a BFS is a lot easier to read, and in a DFS you have to implement a whole function, it's recursion, and to those who's not familiar to it, I'd really much rather prefer a BFS. So we're gonna go ahead and do a BFS. So BFS over the tree, only add the values, inclusive low, high, only search values if the root of cur value is left of cur node if cur val is greater than a low. And it says only search values right of curve node if curve value is less than high. It has to be less than. It can't be less than or equal. If it's equal to 15, like in this case, if it's 15, I wouldn't search anything to the right. So it has to be less than. Because if this was a 14, then a 15 could be here, right? So that's the pseudocode. And yeah, we'll analyze your time complexity is potentially O of n, where n is the number of nodes in the binary search tree. I mean, the whole thing could be inside of it, so I say O of n. Space complexity, like we said, O of w, where w is the width of max width of binary tree. Okay, so let's go ahead and instantiate our queue structure. Let's go ahead and queue up our tree node object. So tree node, let's say I call it our queue. Queue.push root. And then we'll say while queue dot is not empty, we'll say queue dot front, right? CPP queue, this should be front. Yes, front. So pop does not return anything. That's right. So we have to say tree node cur is equal to queue dot pop or queue dot front and queue dot pop, and then if cur, we'll have an int sum. So 0 if queue value, right? Queue value. Low and queue value is less than or equal to high. Sum plus equal queue value. Okay. Then we have to figure out which parts of the left and right do we want to pin. So we talked about it. So if qval is greater than low, then we will go ahead and let me say cur. I got confused here. So cur value is greater than low. Then we say q.push cur to the left. If value is less than high, then we can go ahead q.push cur to the right. So we do that and we turn this on. So that's the code kind of done already here. So if we walk through our example 1, we start with 10, and then we add 10 to the queue. Sum is equal to 0, cur is equal to the front node, so 10. And then we say, okay, is 10 between 7 and 15? It is, added to the sum. Sum is now 10. Is this value greater than the low value? It's low 7, it is, so we can push the 5. And then we say, okay, is this cur value less than the high? The high is 15. If that's the case, we push the right. Go to the 5, it's not within the range. This check fails because 5 is not greater than 7. So, but this check succeeds, so we can push the right node. Here, for our 15, cur value is that it's within the range, so we add it, so this becomes 25. So then cur value is greater than low. Yes, we push a null pointer on there. So let's make sure we check if cur left and if cur right and. So now we won't push any null pointers on there. Okay, and this check fails because 15 is not less than 15, so we don't search on the right. And that ends it, so we'll return. Then we go to the 7, and then we add 25 plus 7 to get 32, and that's the case. And same thing here. So 10, 5, push 7, push 6. So that is it. That's our BFS implemented very straightforwardly. CPP one-line if statements. I wonder if there's a cleaner way to do this. Having these guard if statements, I'm sure there's a cleaner way to write them. But I think this is pretty clean as is. How am I doing on time? Let's see. We are recording for 11 minutes, so that's pretty good considering I explained everything. Let's go ahead and add some more test cases. Can never hurt to have too many of those. 1, 6, and 10. Let's make this 1 and 1. And then let's make this 1 and 2. And then 1, 2, 3. This 1 and 2. So. Tree root is not a binary valid search tree. Right, my bad. So this should be 1, this should be 2. Okay, and accept it. So let's go ahead and submit our answer, and that should be it. Voila. So it says we beat about 13%, memory is 64%. So I noticed that DFS solutions typically will actually run a lot faster. Oh, this is a very recursive solution. Yep, it's DFS. DFS solutions tend to run faster than breadth first search. Sum up if root low high, root low. So this is also DFS. That's yeah, this is a BFS. They use a stack. Well, it doesn't matter what you use. Okay. I guess for the sake of demonstration, we can also do a DFS solution. So they had a great idea. H is the binary tree. Say diff over tree. Skip over DFS if low. Skip left if low is if cur is greater than low is less than, because you don't want to find any smaller values. Skip right if cur value greater than high, some values. Okay, and as I've noticed, cheating a little bit, looking at the solutions, I don't have to create a separate function. This is a very simple, you can use the DFS function for recursion. So we're going to go ahead and do that. So we are going to say if root value is less than, is within low, root value is within high, we're going to say int plus equal root value. Return root value plus range sum BST. Root. Well, here we know that that it's greater than the low value. So if it's greater than the low value, we can look left. And it's less than the high value, so that means we can also look right. Root right, no, high. Else if no is equal to root. If not root, return 0. So if it's such that it's greater than high, then we can only return root that goes to the left, no high. Else if right. Return range sum BST root right. So is there a case where I return neither one of them? So the case is, okay. Well, if I have a 5, even if I have like a 3 or I have like a 5,000 here, I still want to look left. Because what's possible is that there could be values left of 5,000 and in between 10. So this actually just becomes a couple blocks. Well, it must be this is actually inefficient. Actually, I think this should work because look, 10. Okay, 10 is in between, so I do left and right, so I go left. And then I say, okay, that's not in between, but it is, so then we only look right. So 7, oh, that's in between, let's return left and right. Go up, oh, now we have 7, now we go to the 15. 15 is within the values, so I do left and right. And I did waste some time going right here. But it's a very elegant solution though. I wonder how fast, much faster this is. So it beats 16.71%. How are these people getting it so fast? In order. Huh. Gotcha. That's how they cut it down by a third. Oh well. So that is an implementation of TFS. That's the 20-minute mark. I'm going to go ahead and stop the recording. Hope you learned something from this.